Element 5.3. Radiation. In this session, you will develop an awareness of the following types of radiation and its various health effects. Typical occupational sources of non-ionizing and ionizing radiation. And the basic ways of controlling exposures to non-ionizing and ionizing radiation. Radiation comes in various forms, each with distinct characteristics and properties. The primary types include alpha, beta, and gamma radiation, which are commonly associated with nuclear processes. X-rays, renowned for their medical applications, possess high energy and penetrate matter effectively. Neutron radiation involves neutrons emitted during nuclear reactions, contributing to unique challenges in radiation protection. Ultraviolet radiation, emitted by the sun, can cause skin damage and is commonly associated with tanning beds. Infrared radiation, experienced as heat, is emitted by warm objects and is essential in various technologies. Lasers produce coherent and focused light beams, with applications ranging from medical procedures to communication. Microwaves, used in household appliances, are a form of non-ionizing radiation with lower energy than visible light. Understanding these diverse types of radiation is crucial for assessing their distinct effects and implementing appropriate safety measures. Ionizing radiation encompasses various particles, each with distinct properties. Alpha radiation involves particles comprising 2 protons and 2 neutrons, forming helium nuclei. Despite limited penetrating power, approximately 2 centimeters in the air, alpha radiation is potent and is utilized in smoke detection devices. Beta radiation consists of high-speed electrons with greater penetration, around 800 millimeters in the air. This type of radiation finds applications in thickness measurement equipment. Understanding the characteristics of alpha and beta radiation is essential for implementing safety measures and employing their unique properties in specific technological applications. Gamma radiation constitutes high-energy electromagnetic wave emissions, distinguished by its deep penetration of approximately 30 meters in the air. This type of radiation is instrumental in applications like radiation photography, particularly in non-destructive testing scenarios. X-rays, on the other hand, are emitted during specific changes in the energy levels of orbiting electrons. With high penetrating power, X-rays can traverse various materials, making them invaluable in medical photography for diagnostic purposes. Understanding the characteristics of gamma and X-rays is crucial for utilizing their penetrating abilities effectively in applications ranging from industrial testing to healthcare diagnostics. Neutrons, characterized as elementary particles with unit atomic mass and no electric charge, exhibit very high penetration capabilities. Their application is particularly notable in nuclear reactors, where their unique characteristics play a crucial role. Radon, on the other hand, is produced through the decay of the unstable isotope radium, and is commonly found in environments like mines, stone quarries, soil, and rocks. The main routes of entry for radon are inhalation and ingestion, emphasizing the significance of monitoring and controlling exposure in environments where radon concentration may pose health risks. Understanding the properties and sources of neutrons and radon is essential for effective radiation safety measures and risk management. Exposure to various radiation sources can result in a range of health effects, including radiation sickness, which may manifest with symptoms such as nausea, vomiting, and diarrhea. Additionally, skin-related issues such as blistering, ulceration, and hair loss may occur. Other health impacts include dermatitis, the development of cataracts, a white layer in the eyes, anemia, a deficiency of red blood cells, increased risk of cancer, genetic mutations, and the potential for birth defects. Understanding these health effects is crucial for implementing effective safety measures and protective protocols in environments where radiation exposure is a concern. Occupational sources of radiation exposure encompass a variety of industries and activities. These include non-destructive testing of welds, where radiation is used to inspect the integrity of weld joints. Density measurement processes also involve exposure to radiation, especially in fields like construction and material testing. Workers in nuclear power stations, who are involved in the production of nuclear energy, encounter occupational radiation exposure. In the medical field, both diagnosis and treatment procedures, such as X-rays and radiotherapy, expose healthcare professionals and patients to radiation. Underground miners, due to the presence of naturally occurring radioactive materials in certain mines, and aircrew, who may be exposed to cosmic radiation at higher altitudes, are additional examples of occupations with potential radiation exposure. Proper safety measures and monitoring are essential in these workplaces to mitigate the risks associated with occupational radiation exposure. Radiation control involves employing various measures to minimize the exposure of individuals to harmful radiation. The key principles of protection include managing time spent in areas with radiation, increasing distance from radiation sources, and employing shielding materials to attenuate radiation. Enclosure of radioactive materials or sources is another method to limit exposure. Additionally, the use of personal protective equipment, PPE, designed to block or reduce radiation exposure is crucial. Regular health surveillance of individuals working in radiation-prone environments helps monitor and address any potential health impacts. Implementing these control measures ensures a comprehensive approach to safeguarding individuals from the adverse effects of radiation in occupational settings. Non-ionizing radiation encompasses various forms, each with distinct sources and potential health effects. Ultraviolet, UV, radiation, emitted during welding and sun exposure, is associated with skin burns and an elevated risk of skin cancer. Lasers, prevalent in the construction industry, welding, and medical surgery, may cause mild retina burns and, in severe cases, permanent blindness. Infrared radiation, arising from the sun, furnaces, heated metals, and welding arcs, can result in skin redness, burns, and cataracts. Microwaves, produced by radar, drying processes, and microwave ovens, have the potential to cause skin and eye burns. Radio waves, generated in radio transmission and radar operations, may contribute to organ failure. Understanding these sources and their corresponding health effects is crucial for implementing effective protective measures in various occupational settings. Monitoring is a crucial component in safeguarding occupational health and safety, particularly in the context of radiation protection. It serves to verify the effectiveness of hazard controls, ensuring that designated areas are accurately assessed for existing radiation hazards. The monitoring process detects any breakdowns in control measures or systems, providing essential information to address potential issues promptly. It plays a pivotal role in ensuring that workers adhere to established radiation protection controls and promptly report any defects or irregularities. Moreover, monitoring is essential for enforcing the use of personal protective equipment where mandated, contributing valuable insights to identify individuals at risk who may require specific health surveillance due to potential radiation exposure. By maintaining a consistent and thorough monitoring regimen, organizations can proactively address radiation safety concerns, promoting a workplace environment that prioritizes the well-being of all employees. Health surveillance, in the context of radiation, involves various checks and assessments to ensure the well-being of individuals exposed to potential radiation hazards. Skin checks are essential to monitor for any signs of radiation-related skin issues, such as burns or dermatitis. Respiratory checks help evaluate the impact of radiation exposure on the respiratory system. The health surveillance process includes a thorough reference to exposure records, providing a comprehensive overview of an individual's history of exposure to radiation sources. Additionally, referencing sickness records helps track any health issues or symptoms that may be related to radiation exposure, enabling timely intervention and appropriate medical attention. Through systematic health surveillance measures, organizations can actively manage and address potential health risks associated with radiation exposure, promoting a safer working environment.